Imagine this. Somewhere in the universe, something is calling. Not once, not twice, but over and over again, every 16 days. For years, astronomers believed the sky was filled with random bursts of radio noise, brief flashes arriving from unimaginably distant galaxies before disappearing forever. They called them fast radio bursts, or FRBs. They were among the greatest mysteries in modern astronomy because almost every one of them behaved the same way. They appeared without warning, then vanished. No pattern, no schedule, no second chance. If you missed one, it was gone forever. That unpredictability made them almost impossible to study. Then, everything changed. In 2018, a network of radio telescopes picked up another burst, unlike anything seen before. At first, it looked ordinary, a split-second pulse of radio energy that had traveled across the universe for hundreds of millions of years. But when scientists examined their data, they noticed something impossible. The signal came back. Not randomly. It returned after 16 days, again and again and again. For the first time in history, an FRB wasn't acting like a cosmic accident. It was following a schedule. That discovery stunned astronomers around the world, because nature rarely behaves with such precision on cosmic scales. Something, somewhere, was creating enormous explosions of radio energy, then stopping, only to begin again exactly 16 days later. The object received a technical name, FRB 180916.0158 plus 65. Not exactly memorable, but its behavior would soon become one of the biggest puzzles in modern astronomy. Every cycle followed the same strange rhythm. For roughly 4 days, the signal became active. Multiple radio bursts could appear during that window. Then, silence. Nothing. No detectable activity for about 12 days. Then the pattern repeated. 4 days on, 12 days off, 16 days total, like clockwork. Imagine trying to explain that. A dead star, a black hole, 2 stars orbiting each other, something hidden behind clouds of plasma. Every possibility raised even more questions, because the radio burst itself was already incredibly powerful. Each pulse released an astonishing amount of energy in just milliseconds, enough energy to rival what our sun produces over several days, compressed in less time than a blink. And yet, whatever created those bursts could somehow repeat the process again and again without destroying itself. That alone challenged existing theories. Scientists searched through years of archived observations. Had they simply missed other repeating patterns? Or was this object truly unique? As more telescopes joined the search, another unsettling realization emerged. The timing wasn't an illusion. Independent observatories across different countries detected the same 16-day cycle. Different instruments, different researchers, same result. That eliminated the possibility of equipment failure. The universe itself was producing this rhythm. The discovery spread quickly through the scientific community. Some researchers believed they were looking at a highly magnetized neutron star called a magnetar. Others argued it had to be part of a binary system orbiting another massive object. A few suggested dense clouds of charged particles periodically blocked the signal, creating the illusion of a cycle. Every explanation sounded reasonable, until the evidence began creating new contradictions. Because every new observation solved one mystery and uncovered another. The radio bursts weren't identical. Some were brighter, some lasted longer, some showed complex internal structures that looked almost engineered. Tiny details hidden in each pulse hinted that whatever generated them wasn't behaving randomly at all. The more scientists studied the bursts, the stranger they became. Then came another surprise. Researchers finally traced the source to a distant spiral galaxy approximately 500 million light-years away. Compared to many FRBs, that was practically next door. Close enough for astronomers to examine its environment with unprecedented detail. They expected to find something extraordinary. Instead, the source appeared to sit inside an ordinary region of an ordinary galaxy. No gigantic black hole, no spectacular explosion, no obvious cosmic catastrophe. Nothing seemed dramatic enough to explain one of the most mysterious radio signals ever discovered. That made the mystery even deeper. If the surrounding galaxy looked so normal, why was this object behaving in such an extraordinary way? Then one scientist asked a simple question. What if the 16-day cycle wasn't caused by the object itself? What if something else was controlling when we could see it? That single idea would completely change the investigation and lead researchers towards a possibility that nobody had seriously considered before.
For months, astronomers focused on one assumption. The mysterious object itself had to be turning on and off. It seemed obvious. If a signal appears every 16 days, then whatever creates it must somehow follow that schedule. But science has a habit of rewarding the people who question the obvious. One research team proposed something completely different. What if the source never stopped transmitting at all? What if the radio bursts were happening continuously, but for most of the cycle, something was hiding them from us? That idea shifted the investigation in an entirely new direction. Instead of asking what creates the bursts, scientists began asking what could block them. The answer pointed toward one of the most violent environments in the universe, a binary system. Imagine two incredibly dense stellar objects trapped in an endless dance around each other. One of them could be a magnetar, a neutron star with a magnetic field so powerful it would erase every credit card on Earth from halfway to the moon. The other could be a massive companion star. As they orbit each other, the magnetar continues producing bursts of radio energy. But the companion star isn't quiet. It constantly throws out enormous winds of superheated plasma. Clouds of electrically charged particles race through space at incredible speeds. Radio waves don't pass through plasma easily. In fact, dense plasma can scatter them, bend them, even block them entirely. Suddenly, the 16-day mystery had a possible explanation. The bursts never stop. We simply can't see them most of the time. Only when the magnetar reaches a certain point in its orbit, when our line of sight briefly clears, do the radio signals escape into space and finally reach Earth. It sounded elegant. It matched the observations surprisingly well. For a moment, it looked like the mystery might already be solved. But then, the data refused to cooperate.
Scientists compared hundreds of detected bursts. If plasma was merely blocking the signals, the radio waves should become distorted in predictable ways as they passed through different amounts of material. Sometimes they did, sometimes they didn't. Even stranger, several bursts appeared far brighter than expected, almost as if something wasn't blocking the signal, but amplifying it. That possibility introduced another bizarre phenomenon: gravitational lensing. According to Einstein's theory of general relativity, massive objects don't simply exist in space, they bend space itself. Light bends around them. Radio waves bend around them too. Under the right conditions, a massive star can act like a gigantic cosmic magnifying glass. Could the companion star occasionally focus the radio bursts toward Earth, making certain signals appear dramatically brighter? Researchers built computer simulations. Some matched parts of the observations, others failed completely. No single model explained everything. Then another clue emerged from inside the bursts themselves: their polarization. Radio waves carry information not only through frequency and brightness, but through the direction in which they oscillate. Polarization is like a hidden fingerprint. As radio waves travel through magnetic fields, their polarization changes. By measuring those changes, scientists can estimate the magnetic environment surrounding the source. The results were astonishing. The magnetic fields near FRB 180916 were incredibly complex, not chaotic, structured, layered, dynamic. It was as though the radio waves were weaving through an invisible maze before escaping into space. That pointed once again toward a magnetar, but not an ordinary one. If a magnetar was responsible, it existed inside an environment unlike almost anything astronomers had studied before. Then came another surprise. Other repeating FRBs started appearing. Not many, but enough to change the conversation. One repeated every few days. Another followed a much longer cycle. Others showed no obvious rhythm at all. That meant the 16-day signal wasn't a one-of-a-kind cosmic accident. It belonged to an entirely new category, repeating FRBs. And suddenly, scientists faced an uncomfortable realization. Maybe they hadn't discovered one mystery. Maybe they had uncovered an entire population of mysterious objects hiding throughout the universe, each one behaving differently, each one refusing to fit neatly into existing theories. As observatories around the world continued listening, patterns began emerging. Some repeating bursts originated inside regions where massive stars had recently died. Others came from surprisingly calm galaxies. The environments didn't match, the ages didn't match, even the burst energies varied enormously. Every answer produced two new questions. Then one observation caught everyone's attention. During one active window, several bursts arrived unusually close together, almost like a rapid-fire sequence, not evenly spaced, not random either. The timing looked strangely organized, enough for some researchers to wonder, could whatever drives these bursts become unstable during certain orbital positions? Or was there another hidden cycle buried beneath the 16-day rhythm? Scientists weren't looking at just one clock anymore. They might be looking at multiple clocks operating simultaneously. And if that were true, the mystery had become far more complicated than anyone imagined. because somewhere inside those overlapping patterns was the real mechanism behind one of the universe's most extraordinary repeating signals. And finding it would force astronomers to challenge assumptions they had trusted for decades.
By now, the 16-day cycle had become one of the most closely watched mysteries in astronomy. Every time the active window approached, radio telescopes around the world prepared to listen. Scientists knew they only had a few days. If the signal appeared, every second of data mattered. If it didn't, they would have to wait nearly 2 more weeks for another chance. This rhythm transformed the way astronomers studied the source. Unlike most fast radio bursts which struck without warning, FRB 180916 gave researchers something incredibly rare: a schedule. That schedule allowed multiple observatories to point at the exact same region of space simultaneously. Radio telescopes, optical telescopes, X-ray observatories, even gamma-ray detectors. The hope was simple. If another type of light appeared at exactly the same moment as the radio burst, it could finally reveal what was creating it. The countdown began. The active window opened. The first radio burst arrived, then another and another. The radio telescopes detected them perfectly, but every other instrument saw nothing. No bright flash in visible light, no powerful X-ray explosion, no burst of gamma rays, just silence. It was one of the most frustrating results scientists could imagine. Something was releasing enormous amounts of radio energy, yet leaving almost no trace across the rest of the electromagnetic spectrum. It was like hearing thunder without ever seeing lightning. That unexpected silence forced researchers to rethink their assumptions once again. Maybe the object wasn't producing all forms of energy equally. Maybe the radio bursts were generated through a process unlike anything previously observed. Then another discovery complicated the story even further. When scientists measured the exact arrival times of individual bursts, they noticed something remarkable. Even after traveling nearly 500 million light-years, the signals remained incredibly sharp. If they had passed through large amounts of turbulent matter, they should have become smeared and distorted. Instead, many bursts arrived with astonishing clarity. That suggested the path between the source and Earth was surprisingly clean, which raised an uncomfortable question. If dense clouds of plasma were hiding the signal for 12 days, why weren't they leaving stronger fingerprints on the bursts we could see? The plasma model still worked in some situations, but not all. Again, the evidence refused to fit neatly into one explanation. Then researchers turned their attention to the source's neighborhood. The repeating signal came from a region where new stars were actively forming. That was an important clue. Massive young stars live fast. They burn brightly, then explode as supernovae. What remains is often a neutron star, or, under the right conditions, a magnetar. Suddenly, the magnetar theory gained new support. A young magnetar would possess an unimaginably strong magnetic field. Over time, stresses inside its crust could trigger violent star quakes. Each quake could snap magnetic field lines, releasing a powerful burst of radio energy into space. The idea sounded convincing, until scientists performed the math. The energy budget didn't always add up. Some bursts appeared so powerful that explaining them with starquakes alone became difficult. Could magnetars really sustain this behavior for years, or was another mechanism helping them? The mystery deepened again. Then, in an entirely different part of the universe, astronomers witnessed something extraordinary. Inside our own galaxy, a known magnetar suddenly emitted a fast radio burst. For the first time ever, scientists had observed an FRB from a source close to Earth. It was a breakthrough. The event proved that magnetars could produce fast radio bursts. For many researchers, it felt like the missing piece of the puzzle. Case closed. Except it wasn't. Because the galactic burst looked similar, but not identical. Its energy was much lower than many extragalactic FRBs. Its behavior was different, and most importantly, it didn't explain the mysterious 16-day rhythm. The discovery answered one question, but left the biggest one untouched. What was controlling the clock? If a magnetar was responsible, why 16 days? Why not 15 or 20 or completely random? Nature rarely chooses such precise timing without a physical reason. Some scientists suggested orbital motion. Others proposed that the magnetar itself might slowly wobble like a spinning top. This motion, known as precession, could cause its radio beam to sweep across Earth only during certain parts of the cycle. If true, the object might be transmitting continuously. We simply intercepted its beam for a few days before it pointed elsewhere again. It was an elegant idea, but there was a problem. The predicted motion didn't perfectly match every observation. Some bursts appeared slightly outside the expected window. Others arrived with properties that the precession model couldn't fully explain. No matter which theory researchers tested, the universe always seemed one step ahead. And then, as more years of observations accumulated, astronomers noticed something almost no one had expected. The 16-day rhythm itself might not be perfectly constant. Tiny changes were beginning to appear, subtle, easy to dismiss. But if they were real, then the cosmic clock wasn't as precise as everyone believed. And if the clock was changing, something in that distant system was changing with it. A realization that opened the door to an even deeper mystery.